Hello and welcome to another Stephen Mendes educational video. The next problem the students had on their test was a steady state AC analysis problem. As you can see, the circuit is there, and they were asked to use Norton to calculate Norton's theorem to calculate the current through the load resistor RL, which is marked on the diagram. The first thing the students had to do was, obviously, in doing Norton theorem, they removed the RL completely and replaced the terminals A and B where the RL should have gone, and they would also short out the voltage source so they would have a dead network. Okay, so there is the dead network and the terminals A and B where the load should go. So those are the first two things to do. Remove the load, put the terminals A and B, short out the voltage source, and find the impedance of the dead network. Now, this is not a difficult thing to do, because if you look at that carefully, you can see that between A and B we have three parallel configuration. We have C1 with R1, we have R2 with L1, and then we have C2. So the three of those branches are in parallel. So we come here now, and the first thing we need to do is to work out the reactances of the two capacitors and the inductor at the specific frequency given in the problem. So we take our 5 kilohertz and multiply it by 2 pi so that we find omega in rads per second. And then our formula is J omega L for the inductor and minus J 1 over omega C for the capacitors. So we simply plug our value of omega and C in there, and we find that our capacitor C1 rounds off to minus J2 ohms, whereas our capacitor C2 rounds off to minus J3 ohms, and our reactance works out at J31.4 ohms. We can now assemble our complex numbers for the impedances, because notice with the Z1 we have the resistor 10 ohm here in series with the C1 16 microfarad capacitor. So the real part of that impedance will be 10 for the 10 ohm resistor, and the imaginary part will be the minus J2 ohms for the capacitor, and that will be our impedance Z1. When we come here for Z2, we have a real part of 15 ohms and an imaginary part of 31.4 ohms for that parallel branch that I'm showing you there with the arrow. Now when we come here now for the third, there is no resistor in series with our capacitor, so that means that the real part is going to be 0, and we just have minus J3 as the impedance of the capacitor. So what we have to do is we have to use our parallel formula, which works just as well with resistors as it does with impedances. So we take 1 over each impedance, and then we take the reciprocal of that. And when we do this equation here, which I'm showing you with the arrow, when we do that for these three complex numbers that we have here, Z1, Z2, and Z3, we end up with this complex number in the rectangular form and this complex number in the polar form. Remember, the polar form has an angle and a magnitude, whereas the standard rectangular form has an x and a y component, whereas the x is the real one and the y is the j, or imaginary number. So that is that with that. We have found the ZT is actually what would be the ZTH, or the Thevenin equivalent resistance of the dead network. We now proceed to discover the ISC, or short circuit current, for the system that we're trying to analyze. And this is even so much easier that students should have really been excited, because when they short A and B, as I have done here, notice I have shorted. I've shorted A and B. The terminals are shorted, which means I've actually completely shorted out C2, and I've also shorted out R2 and L1. And because the short circuit current is coming right down here, it's just a piece of wire, and it's the main circuit. Look at how I've redrawn it. The short circuit current, it's just a simple series circuit with C1 and R1, and the other difficult hard components have disappeared. So once again, we have a complex impedance which has 10 as the resistor value for R1. And we have our minus J2 as the reactance of the C1. And we were given in the problem that we had 8 volts with an angle of 60 degrees. So we just divide the V1 by the Z, and lo and behold, out pops our short circuit current, which is the Norton current, of 0.784 with an angle of 71.3 degrees. Finally, we can draw our Norton equivalent circuit with the ISC and the ZTH. Don't mind I wrote RTH there. I'm thinking in terms of just the resistor one. So when it is done with AC, it would be ZTH. But we've worked out the ZTH and we've worked out the ISC. So all it remains now is for us to stick our load resistor there as shown. And once we can find the current through our load resistor, we're good to go. So now what do we do? Well, we come down here, as you can see, and we write the current. This is the main circuit current here. This is the ISC, the source of current that's powering the entire circuit. And this term over here is basically the current divider. Remember, we have the other resistor over the sum of the two. So this one here is the ZTH over the ZTH plus the RL. And that fraction multiplied by the total power circuit current gives us an I of 0.11 at an angle of 7.2 degrees of current through the load RL equals 20. And once again, we are completely finished with the problem. So now you should be uploading your work, finished with your test. But because I'm teaching you here quickly, we're going to do it not with the Norton, just by the normal method, which makes it a little more difficult because you have a few more complex numbers to manipulate. So suppose we didn't want to do it by Norton and we said we're just going to analyze the circuit just as it was given. We still have 3 parallel impedances, but now our Z1 is the 15 with the 1 millihenry coil. Our Z2 is the load that we had removed. Our Z3 is C2. So we've written our Z1, Z2, and Z3 there, and we once again have found the total for our parallel combination, this time including the Z2. 20 ohms with no imaginary part. 20 ohms with no imaginary part as shown there. And so the procedure is quite similar to what you did before. And then you want to find the total circuit current. So what have we got? Well, we've got V over Z to get I. We have, in fact, got the voltage here over the sum of all the impedances around the series circuit. So the first one here is just the reactance of C1. Then we have our parallel impedance that we just worked out for Z1, Z2, and Z3. And then finally we have the 10 ohm resistor that completes the circuit back to the source. And that gives us a total circuit current of 0.68 with an angle of 85.7 degrees. Now we work out the voltages across each of those components. The voltage across R1 will simply be the circuit current multiplied by R1. The voltage across the combination will be the combination impedance times the current. And likewise, the voltage across C1 will be the C1, the Z or impedance of the C1 times the circuit current. So those are the voltages across the parallel combination, the C1 and the R1. Well, the one that we're interested in, of course, is the parallel one. So we take the voltage across the parallel one and we divide it by the actual resistance of the load. So then we find the current through that particular element, because all of the three of them have the same voltage across them. So once we've worked out the voltage across the parallel combination, all we have to do is divide that voltage by the resistance, the 20 ohm resistor, which is what you can see here in the bottom. So that's the voltage across the parallel combination. That's the voltage across the resistor. And boom, we get our same current, 0.11, with an angle of 7.2 degrees, just as expected. And once again, we are 100% certain that our Norton problem was done correctly, and we can expect 100% from this test. So thank you so much for watching, and we'll see you in the next video.